Diffusion is an essential transport process that occurs frequently throughout our everyday lives. Today we will be examining this fundamental process and how it is affected by molecular weight. Diffusion is the natural tendency to transfer a species in a mixture from an area of high concentration to a region of low concentration. This difference in concentrations is known as the gradient and is the driving force behind mass transfer. Particles will move in this fashion until they reach equilibrium. As seen in this animation, the green particles start highly concentrated within the bottle, eventually moving out into the open system. This is done until there is an equal concentration of green particles in and out of the bottle. Most diffusers, including the one seen later in this video, use an ultrasonic atomizer to create the mist that comes out of the diffuser. Inside the diffuser, there is a little metal flap that vibrates at an incredibly fast speed. This speed makes the droplets of the liquid extremely small, creating the mist. The mist is then pushed out of the diffuser due to the pressure buildup within it, sending the droplets up and out of the diffuser. These droplets then diffuse into the ambient air. That behavior is later being simulated using COMSOL to show how diffusion coefficients and molecular weight can change the way this mist diffuses into the air.
There are many applications of diffusion in daily life. One example is air fresheners, which we plug into a wall and let them diffuse their active odor-trapping molecules so that bad smells are sequestered and disappear. Air freshener companies want a faster diffusing molecule so that odors are eliminated quickly. Other types of industries want a different effect out of their product. Perfume companies create sprays that are designed to minimize the diffusion of the perfume molecules. If the perfume molecules are designed to diffuse slowly, a longer-lasting scent can be maintained. We plan to investigate the effect that molecular weight has on diffusion. If a correlation between molecular weight and diffusion rate is found, diffusion properties can then be purposefully modified through molecular weight. By using different molecular weights, a molecule can diffuse either quickly or slowly, depending on what the manufacturer would like their product to do. We conducted two experiments, a computational analysis and a physical test. The computational analysis involved simulating the diffusion of particles throughout a room using COMSOL. In the physical test, we observed the rate of diffusion of two differing liquids through an ultrasonic diffuser.
This part of the experiment was done to qualitatively evaluate diffusion rate based off the length of laminar flow. Liquid tonic water and water were poured into an ultrasonic diffuser. The diffuser then vaporized the liquid and blew it into the open air through a constant airstream. Videos of the gases diffusing were recorded. Tonic water has a molecular weight around 324 grams per mole, while water has a molecular weight of 18 grams per mole, significantly lower than that of the tonic water. A difference in the length of the laminar streams before the gas breaks up into a large cloud was observed. Once the gas forms this large cloud, the flow is considered to be turbulent and disorganized.
As you can see in the videos, tonic water has a much longer laminar stream. The laminar stream is longer with tonic water because diffusion takes longer in the heavier fluid. The tonic water has a lower concentration gradient compared to water, which has a shorter laminar stream, and thus a higher concentration gradient.
Along with the qualitative experiment, COMSOL simulations were run to quantitatively capture the concentration gradient over time. The COMSOL simulations simulated the area directly above the diffuser where the vapor trailed off into the surroundings. The simulations were run across a multitude of diffusion coefficients to observe the difference in the concentration gradient over time. These time-dependent studies show how the gradient develops as time progresses. Notice how the gradient changes differently depending on the diffusion coefficient. Also, see how the concentration profile evolves over time. For example, these first two plots were generated for a diffusion coefficient of 1e minus 6 meters squared per second. And the second round of plots were generated for 1e minus 4 meters squared per second. Each has a concentration profile develop and then later change as time increases. Now we can compare the differences in concentration gradient as the diffusion coefficient changes. This picture shows the concentration gradients for each diffusion coefficient at the same time of 500 seconds. The smaller diffusion coefficients, like 1e minus 9 and 1e minus 8 meters squared per second, do not show any significant concentration gradient, whereas 1e minus 5 and 1e minus 4 meters squared per second show more extensive diffusion. 1e minus 3 shows the 2D area as completely full of the starting concentration of 500 moles per meter cubed. Overall, these COMSOL simulations show the impact that diffusion coefficients have on the diffusion into the ambient air.
In both the COMSOL simulation and physical experiment, bulk flux is ignored, since there is no change in velocity. So the only thing contributing to mass transfer is diffusive flux. The overall equation used to describe the change in concentration caused by diffusion is Fick's law, with JA being mass transported by diffusion, DAB being the diffusion coefficient, and del C being the concentration gradient. In Fick's law, the proportionality constant in a binary mixture of species A and B is known as the diffusion coefficient, DAB. To solve for the diffusion coefficient, the Hertzsprung-Felder equation can be used, assuming the mixture is a binary system composed of rigid spheres. The equation is as follows, with T being temperature, MA and MB being molecular weights of species A and B respectively, P being pressure, and sigma AB being the collision diameter of A and B, and finally omega D being the collision integral for molecular diffusion. This equation shows how the diffusive coefficient is inversely proportional to the molecular weight of species present. Graham's law is a simple way to relate molecular weight to the diffusivity rate. The rate of diffusion of a gas is inversely proportional to the square root of the molar mass and its particles, with R1 and R2 being the rates of diffusion of species 1 and 2 respectively, and M1 and M2 being the molecular weights of species 1 and 2. This equation also shows the diffusion dependence of molecular weight. All of these equations can be compared to the COMSOL simulation and the physical representation to verify their accuracy. The higher molecular weight molecules diffuse more slowly into their surroundings, while the lower molecular weight molecules diffuse more rapidly into their surroundings.